I should be. So, good.
So, yeah, this is kind of like, I think, more related to the consensus design itself rather than the broadcast strategy or the propagation strategy that we are looking for. So, clear. I mean, sounds like one to n is always looks better. Like just by. I mean, I'm not talking about. I'm just talking about from the communication complexity. No, I'm not talking about from the consensus point of view. Maybe there is the end-to-end design makes it faster for the consensus for some other properties that it has. But from the just network and communication point of view, it sounds like one to n sounds better. Um, so that's what I think. But is it like kind of like related to Monad is doing one to n, and like maybe there are some end to n approaches like Autobahn. I don't know. I wasn't familiar with like details of like the Autobahn. So yeah,
Yeah.
Um, so I mean, I think that it's pretty clear. Like if you're angling for like max throughput, that like having n concurrent lanes of broadcast can be much more. The challenge becomes like how do you think about an account model and ensuring that the quality of those n concurrent broadcasts is high enough that it's better than just having one lane that you can actually enforce like different sort of state conditions on has been our kind of assessment of it. It should be clear though, even if you have n lanes and you have like some sort of agreement protocol, it's still critically important that the whatever the block data is, even if it's certificates, gets to everyone very quickly. And so you don't necessarily have to treat them exclusively. Like if you have an encoding scheme that ensures that if something is broadcast and people all see it, that everyone sees it within some kind of range, can still be a really nice addition to like a standard agreement protocol that is using something like an Audubon-like construction to ensure that data can get to everyone, and that if you vote, that most people have seen it. So I don't know if it's strictly different, but I think the approach Monad's taking, for example, definitely gives you really awesome latency in the consensus finality case. But from a user perspective, you can simulate different sorts of finality conditions using like an Audubon confirmation receipt much faster than you would have consensus if that's interesting in whatever your application is.
yeah.
So I'm not sure they're mutually exclusive in each way. I would love to get your take on it.
I actually want to say they're not exclusive. I think typically, if you compare DAG-based systems on one side that require everybody to act as a broadcaster, and you compare a single leader-based consensus protocol, that's a trade-off between latency and max achievable throughput, perhaps. But it's not always a good thing to have everybody act as a proposer. If you have heterogeneous participants, okay, you have to worry about the quality, you said. You also have to worry about the quantity, right? Not everybody produces the same amount of data. Maybe, one replica is in a more geographically remote location, therefore, they have the highest tail latency, so they would be a bottleneck if I require everybody to broadcast. So that's actually a con of rigid designs. One thing I didn't mention in the talk is that Autobahn is actually not a rigid design. So while we do allow everybody to act as a lane, how much you produce in those lanes can be flexible. And it could be nothing. And you can actually configure that at the consensus layer and require, how much progress do I need in each lane to participate? Do I want to issue the next consensus once I have, 5 new data items in lane 1 and 2 in lane 2 and 0 in the others? That's fine. That's something you can't do in that protocol, and I think it's actually a hindrance. If you're not bottlenecked on throughput, say you're bottlenecked on execution, and you have more than enough transactions to send anyways with a single proposer, you shouldn't force multiple replicas to act a proposer for the sake of it. You should give the opportunity, because that allows your system to scale dynamically with your workload, and that I think is the important part.
So, and also one thing to add is like we are kind of like, I mean, I didn't understand your question mostly was about the networking layer or it was consensus layer, because if it was about network and like the propagation, we are kind of like transforming one to end to end to end. So like instead of just sending from leader to all the validators, the leader sends to end validators and then they send it to each other. So it sounds like end to end definitely looks much better from the communication point of view. So, but yeah, I mean, from the consensus point of view, that's I mean something else that they talk about.
Yeah. Yeah.
One interesting adaptation we've actually thought about doing for some of the Autobahn stuff is in the right sort of heterogeneous network configuration, requiring some minimum number of certificates to be included to have some notion of like fairness for like running an auction.
So we have this lane coverage
Yeah.
parameter.
Yeah.
By default, we said we require 2 of +1 lanes in advance, just so you know at least half of it came from good guys.
Yeah.
But you can configure that however you want. And that's a trade-off between fastest latency.
Yeah.
And if you have one lane that's going super fast, maybe you want to do consensus more often to allow that lane to commit. You can do that flexibly. But it's always a trade-off between latency, throughput, and fairness. But we allow you to configure that explicitly.
Yeah.
Right? So you can make the choice yourself and you can change that choice.
I want to ask another question about the how erasure coding helps this efficient propagation of data as well.
Yeah. So without erasure coding, that means like we have no encoding. So if we have no encoding, that means that we need to send the data without any encoding. That means like if any chunk of that data is lost, you cannot recreate the data. So one way is to use TCP or request for that chunk, and that back and forth adds like 2 latencies to the communication, which is not desirable at all. Or you can just solve it with some very big redundancy, like maybe in the range of like 100 or something like that, because to kind of achieve the fault tolerance. Because if, for example, if one chunk is lost, if you are supposed to receive, let's say, the first chunk from like 3 validators, if 3 of them are all down, then you won't get that chunk. And if it's not, and then you are not able to decode. And so if it's UDP and it's not TCP, you're not supposed to request for that chunk, and you probably you are not able to get the block at the end. So it's kind of a must, I would say, in case of usage of UDP. So in ETH, they may use TCP, and then there is no encoding. The block size is small. So, but if the block size is higher, and we want to just transfer the block efficiently, definitely we need erasure coding.
Yeah. Thank you. So I think I want to move on to the other topic, which will be like separation of like transaction and like consensus layer. So I think I want to ask whether like block propagation is really a bottleneck. So as you might, I think you already shown that like when we have like 1,000 validators, you said that it takes like 16 seconds. So that's a real bottleneck there.
Right.
All right. So we solve this with like this kind of like erasure coding and like more like a hope networking, and then I think like on this like autobahn kind of like design, you do more on the like end-to-end gossiping, so that you don't have this kind of like bottleneck.
So, yeah, what is the question? Is to
Yes, so yeah, I think like I'm answering my question actually. That's the real bottleneck, and you guys are solving it, but we have different problem with the end-to-end gossiping, and then that's also like very parallelized as well.
right. So I can talk about one. I mean, it's not that good to combine like consensus layer with networking layer. There are some issues always with that. So I mean, In Monad, we can achieve like one round finality if we combine these two. Because of the Raptor cast, because of that end-to-end communication that we have, we can combine them with some extra redundancy to achieve one round finality. But we are not willing to do that because we don't want to combine these two layers, and because it comes with some issues. Like whenever you want to improve your network layer, then you need to also change your consensus layer. So that's something that we want to avoid. So regarding regarding the decoding and like having just one-to-end system, I would say like having in general adding hops is not always good. So in my opinion, just one hop is enough. So adding one more hop is enough. Like having two hops design. The reason that we are adding that hop is to kind of being able to enable the leader to use the bandwidth of all validators. It's not like adding hops is something good.
Yeah.
So that's why actually, if you have noticed, like Solana was using Turbine for a long time, and Turbine has more than two hops. It has three hops or even more. So, but recently, I think a couple of months ago, they have switched to Rotor, which is a two-hop design. So the only benefit that I can see with like Turbine over Rotor is it kind of like puts the high-stake validator higher in the tree, and they get the kind of like the proposal message earlier, and they can vote earlier, and they can achieve consensus sooner. But we can achieve that with some sort of like ordering during that two hop. So we can have two hops, but still when they are rebroadcasting, we can ask them to send those chunks earlier to the next leader and high stake validators. They don't need to just rebroadcast it just randomly to all the chunks. We can just order based on their stake value and kind of the next leader to achieve consensus earlier. So that gives us all the thing. We don't need to pay one more round of latency to achieve that.
Yeah.
So yeah.
The best argument I've seen for like actually stitching together more of the layers is there's this new group of papers that started to come out towards the end of last year called Zoda and the Accidental Computer. And the idea, it doesn't use Raptor codes, but it uses like polynomial style coding schemes. And the idea is that you can reuse a lot of the polynomial commitment work in a lot of different ways, and much more efficiently than just like what you're used to see today with Reed Solomon codes. So it's from the author who I know his name's Guillermo. He works at Baincat Crypto, and the first one, it's called Zero Overhead Data Availability. You can basically come up with a coding scheme that in the coding scheme encodes that the code that you received is correct. And then the addendum paper, the Accidental Computer, basically says, well, we can actually encode a proof of correct execution of the transaction into the actual code that's being sent in the chunk. So you basically get a chunk and you verify a set of polynomials that basically says this is a correct piece of a bigger chunk. And if I get enough of them, I can reassemble the whole thing. And then in that, it also is a proof that the broader chunk is actually correct execution as well. And so that's the best argument I've seen for like how you would actually want to create this like more coupled construction between networking and like the transaction layer, because you could actually reuse a lot of the polynomial commitment overhead for one massive kind of chunk thing. Crazy math way above my level of expertise. Highly recommend checking out the paper, Zoda and the Accidental Computer. Yes.
Thank you. So maybe I want to like talk about spam prevention. So I think like when we check the transaction which is valid or not, we need to check maybe the most important thing will be like gas balance check, and then like nonce check as well, and then we also verify signature as well. So I think like verifying signature is like easier to be parallelized because there's no dependency. But I think a problem with the gas balance check is that you need a global view to understand whether like this transaction has enough gas, because like one signer can have like multiple transactions in one block. but like some node does not have the full view of the entire block. So when you have this like parallelized mempool, how you can guarantee this transaction can be passed with enough gas with full parallel computation allowed. So,
You're asking, is the question if the transaction owner has enough funds to do the transaction?
yes. So that's the core part of the checking the transaction, whether it is valid or not, right?
Maybe I can ask this question myself. I'm not really familiar with what is the problem here. Like, can I not just assume, I take the latest state, which is a stale snapshot. I pessimistically assume the current balance is 1,000 less.
Yeah.
And I just check it. Worst thing that happens is I reject a transaction that could be valid. It just retries later. What's
So
the
basically, that is the grand complexity. It's basically how you ensure that quality is sufficient. So this was actually work I did about 2 years ago on like all the attacks you can run on decoupled state machine replication, and like unfortunately, just a stale balance check can be exploited and drive down what I believe to be like honest or like valid transaction throughput down to like 1% or less. And so I argue that you need to have a more aggressive or like active position on like how you manage that problem. But some people would say, like I think Solana, for example, and like the multi-concurrent composer stuff that they're doing is basically like, well, you get charged for like how many chunks or like lanes you end in concurrently. And well, it's kind of out of your control then how much you get charged. And first off, and so you end up needing to have some sort of either partitioning of accounts so that accounts can only end up in certain things at certain times. You need to have some sort of blocked balance that ensures that your balance is payable up to some point at some time. Or you need to like rigidly assign people to certain sequencers where they have a relationship.
So like an example would be I take my gas balance,
Yep.
I shard it into 5 pieces, I select them round robin for my transactions so that I actually have a fresh and not stale view.
Exactly. So the idea is that you just want to make sure that the block producer or like the one that orders transactions can't get ripped off, I think is like the way we've thought about it. So you want to make sure they can always pull from some balance. And so one way to do it, is say like, okay, the balance that this guy can pull, that he can track how many pending transactions are in flight from.
It's basically locking up your gas funds into future escrow.
I think is one good way to put it. It's almost like you could say, it's almost like an account fraud proof is what I call it. Where it's like you basically lock up the balance, and then if you can spend against it or you're invalid, the producer can pull some amount of funds from that.
What I was going to say is you could say, I registered this amount of gas that cannot be spent before a certain slot.
Yeah.
That guarantees me that it's not the stale.
Then the trick then is you have to make sure that the number of total in-flight transactions is still capped by some amount, and that your max fee per transaction is still within some range to make sure it can cover. I think the problem with all like the thing that Monad has, or like a lot of these ones where the chain is there is no like crazy DSMR like pre-processing step, is that you can avoid a lot of this like transaction complexity with like fee balance tracking that ends up making it much more straightforward. I think you guys still have some asynchronous execution though somewhere in there with like I think the terms like carriage cost is like kind of what you guys use for some.
I am not that much familiar with that part, but I think you're right.
Basically, it's just making sure that somehow you can keep the fee payable. I think. I think that's still a very open question around how to best solve that with like a UX that is convenient for users.
So I think like one of the interesting thing going on with this industry is that like a lot of like decentralization technology is evolving. However, there is some chain who is going backward, more centralization. For example, something like Hyperliquid. But like in the market and from the user base point of view, it's accepted quite well right now. So I am curious about your personal thoughts about like some hybrid centralization is allowable, and even in mass adoption phase, if you have like tens of millions of users, can you really handle this kind of like numbers? And then do you need some kind of centralization in the infrastructure? So that will be my question.
I obviously don't have much experience on this, and I don't know Hyperliquid well, but I think trust is always a tricky question because you have to ask yourself, we like having trust in centralized entities very often. I like when I lose my credit card or somebody steals my credit card number, I just call a centralized party and I get my money back. The question is, can I trust that centralized party? I don't know what is the auditing regulations for Hyperliquid, but our banks are pretty well regulated and held accountable by the government. So that's a chain, it's a root of trust, right? It's like DNS in real life. But and I think that is something I actually liked about the Libra project from a couple of years ago, where you have a lot of big players that can be held accountable. It is centralized in the sense that it's like 50. It's decentralized in the sense that I don't have to trust any given one. If any given one fails, and failing doesn't always have to be for malicious purposes, right? It can be lack of technical aptitude, right? I think the guys at Visa are trash and I'd rather use MasterCard. If I can, pool my trust between them, that's better. So I don't think that's particularly a bad thing. Sometimes it's better than full decentralization. I personally don't find Bitcoin, for example, very trustworthy because I'd rather trust my bank than mining farm in Kazakhstan.
3 mining.
Right, sure, right? So I think perspective matters a lot there.
I think I was having a conversation about this the other day with someone too, because I think it touches on something interesting, which is one, when you trade today, you trust a single company. And so is Hyperliquid, if you compare it to that, it's like, well, it's better. I guess it's more than one entity, although the code isn't public. But if you look at it and try to measure it against like something like an Ethereum, obviously it's a very different feeling. But at the same time, the experience you get from Hyperliquid is not anything close to what you can offer. And so I think the way that we'll see applications develop more in the next few years is this phase of something being live, but pretty centralized, whether that be proof of authority or even like a smaller set of entities that are participating prior to like this open network launch, rather than trying to straight shoot it. Because I think what has happened is a lot of applications think they can straight shoot it and they miss the mark on like what the product is, or they don't have any adoption or any community that's actually interested in securing this thing, and then people just stop caring. And so the idea that you still retain much more ability to move and be agile prior to this like phased decentralization, to me is the journey Hyperliquid is on. I think people love to put them in the bucket of, oh, they're probably done and this is like what they think is decentralized. I don't think that's the case at all. I think that they are like, well, there's a lot still to figure out on the product side, and the more that we're not in control, the more you're not in control to make those product decisions. So I think of it as more of like, well, your alternative is definitely worse maybe, and then you're kind of on this trajectory of, can we make something that is closer to something that we think is more decentralized, but it's not all the way there. And sometimes I think they get put in a corner where people are like, this is the view of decentralization, which I don't think that's true.
So I was thinking that when we have like mass adoption and a lot of users, a lot of like mega apps with like tens of millions of users, I think like this application wants stability of UX for the users, and then that means like guarantee on the block space. But I think like current blockchain structure does not guarantee that, because like it's always competitive with the gas price. That's really like a jungle without any law or like policy. So it's like just economically driven, motivated. So that's quite not organized for mass adoption, I think. So is this like kind of one of the reason why we need centralization? Like 100% control of block space with predefined policies, and who are paying more service fee, then they have better guarantee on the block space. Kind of like a more organized way to create a block. Do you think like this is kind of like important question for mass adoption?
It's like I think, was it yesterday? WorldCoin, like the one that has the orbs, released a thing where basically humans get priority in blocks over arbitrary transactions, which was an interesting take.
Not the MEV, right?
Yeah, it was an interesting take. I'd never thought about doing that. I think what you'll see is over time a continued focus on, instead of just like saying this is a big computer, more and more focused on actually making an experience that is a product people want to use. And I think some of the things that follow from that decision are consistent experiences. And so I think there's either like this world where you have people try to just create their own chains, which is much more expensive and much harder, or you adopt something that what we're interested in, for example, is like if you kind of give applications exclusive access in an Autobahn-like construction, you can have them have much more control over actually how things get sequenced while still being part of like a broader state space. But I think it's something people will want, but there's obviously a lot of benefit to having like an open compute layer and what it lets you do in terms of touching stuff, but you got to pay. And so we'll see it'll be interesting to see how that evolves.
So maybe my last question is around execution bottleneck. So I think we talked about a lot of like consensus layer and data transmission layer, but I think we didn't talk much about the execution layer in this talk. But I think that is also like a huge bottleneck as well. The trivial solution right now is an optimistic parallel execution where you just like assume that there's no data conflict each other, this dependency, and then when you find the dependency, you revert and calculate again.
Yeah.
But like in real life, like one blockchain used to have like mega apps, and then all this transaction is related each other. So that is more realistic assumption and the market situation. So how do you think about like customization of parallel execution when you can build a application in a way so that you can avoid those kind of like data conflict, then you allow this computer to maximize the parallel execution far as possible. So how do you see the future of this industry and the tech stack evolving to build this kind of infrastructure?
I didn't get the fully last part about co-designing, but without talking about blockchains even, most traditional applications today are built around distributed database stacks that are using concurrency control-based mechanisms, right? We do optimistic execution, and we don't try to inherently strip the parallelism of the workload by totally ordering everything. So I think the problem that many of these blockchain-based systems face is you pessimistically funnel everything through state machine replication, right, the total order, because you expect that there are going to be conflicts. Then you hope to recoup some of that parallelism, but then in hindsight, running something parallel. Right? So you funnel things to a bottleneck and you hope to expand. It doesn't really work that way. I think a lot of applications have to ask themselves whether they actually need a log fundamentally. So we talk about blockchain and we mean two things. We both mean the idea of a decentralized system, and then depending on who you speak to, if you spoke to me, blockchain to me is just a different way, a buzzword of describing BFT consensus, which is a total order. But you don't always need a total order, right? The total order is a tool that simplifies things. So I think a future for many applications is to build database first BFT systems that are not using a ledger at the foundation, but offer serializability, the abstraction of a total order directly. So I think that will help, be natural or embarrassingly parallel and not having to worry about these implementation details of how can I recoup the parallelism. Understand that that's not a general purpose solution for existing blockchains today. I think existing blockchains already restrict their transaction model immensely by using stored procedures, right? Smart contracts are stored procedures. Existing applications, again, don't use stored procedures, at least most of the time. If you're already using stored procedures, I think it's not unreasonable that you can estimate, for example, what is your read and write set. Use that to, use a consensus-free path or speed up your execution. I think my bigger answer is to try and think how can you build from transaction upwards and not as an afterthought to consensus.
We don't currently have any execution stuff because we think we're not super thrilled with like where things are currently at. And so instead we focus on P2P consensus and then really high throughput storage. So a lot of the teams we collaborate with have ideas of like how to really change execution. whether it's using, like basically dropping the total order idea, or thinking a lot differently around how things are executed to try and make them more scalable. But I think there's still a lot to explore there, and we are excited to collaborate with teams that are really pushing the needle there, and I think there's still a lot that can be done. I think some people are even starting to do like in that bottleneck phase, like smarter ordering of transactions to like at least try to put them in an order that is more parallel that can be executed. But it's tough to do in a lot of different.
But it can be modeled, but we can also use AI for that,
Well,
AI
and
can
AI there's
train
going to be
it.
probably really difficult to introduce. I think like the way I've seen it is it's you basically give up fairness in a simulation, because then if you like try to avoid the hot path, you just can have a bunch of transactions, but like the hottest or like most popular application is going to be underrepresented based on like the group's want, but like it will be more parallel in the workload. But like you can do a lot of different, like I think some of the applications, let's just say it's not general purpose and you have like something like a trading thing. Like it's much easier to see where the conflicts are, and you can even have like the transactions without any simulation convey what stuff they'll touch. And so the closer you get to like a pure application instance, I think the easier it is to avoid a lot of these problems. But when you have like arbitrary execution on the back end, like there's always going to be some efficiency loss.
Yes.
If you have payments only, you don't need a total order.
Yeah, but I think that's also a really big use case for blockchain too. So I
Payments,
think-
right.
Yeah.
So then those payment systems shouldn't need to have
easy.
a total order.
Yeah.
I think we can wrap up today. Thank you so much for your valuable answers.
Thanks for
thank you
having us.
for having us here.
Thank you.